Hi guys, Dr. Burns here. We're going to take a look at section 3.3, which is where we're going to really get into a little bit more about phase portraits and what those look like for different systems in different cases. The phase portrait, it's really just like a slope field, but it gives you an idea of what the solutions are doing and what those trajectories are going to be. And those are going to vary depending on what your eigenvalues are. So remember we talked about eigenvalues and their corresponding eigenvectors in the last section. We're going to apply that a little bit more here to talk about what those phase portraits are going to actually look like. So there's sort of three main cases when we have real eigenvalues. Now, if we have complex eigenvalues, that's a little different. We'll talk about that in another time. But as long as we have real eigenvalues, there are three cases that could end up. So one is that we could have a lambda value or an eigenvalue that is positive and a second one that is negative. So when the signs are opposite, that's when we get what's called a saddle in the phase portrait. And you can kind of see, I hope in your notes, if you zoom in a little bit, you can kind of see that part of the solutions are going away from the origin and then like this, and that kind of accounts for the positive eigenvalue. And then you've also got solutions that are headed towards the origin. And we'll look at an example of this in just a few minutes. A sink, that's the next case, that would be when both of the eigenvalues are negative. So in this scenario, because the eigenvalues are both negative, remember as time passes on, both x and y are going to be getting smaller and approaching 0. So all of your solutions when you have a sink are going to go towards the origin, basically. You can kind of see that in the picture. Notice these arrows are all approaching the origin, regardless of where you're coming from. And that would happen when both of your eigenvalues are negative. And then the last case, of course, would be where both of your eigenvalues are positive, and that's called a source. Kind of remember that term source, like the source, everything's coming away from the origin this time. So it's the opposite of what you would get with a sink. So all solutions are going to be away from the origin. So x and y are both getting bigger as time passes on. And again, if you look closely here, you can kind of see that all of these vectors are going away from the origin, regardless of where you're starting at. So let's look at an example here. It says, consider this system below, and they've told you that the eigenvalues are -3 and 2. So let's use this to find the eigenvectors that go with it, the general solution, and then take a look at the phase portrait. So let's start with the first one, -3. I'm going to call that lambda 1 is -3. And so remember, to get the eigenvectors, that would be where the coefficient matrix, so in this case the coefficient matrix would be -3, 0, 0, and 2 times the xy would have to equal that lambda value times xy. And remember, just as a refresher, this means that that matrix, that coefficient matrix, times the variable matrix has to equal the lambda value times the same variable matrix. And so we're going to look at the product here, and we're going to write this basically as a linear system. So that would give me -3x, and then of course 0y would equal -3x. You could also, remember, use the other variable, and that would be 0x and 2y would equal to -3y. So either of those would work. Now, this first equation is just an identity, so 0 equals 0. That's not going to really tell me much. But the second equation, we can write this. If I move, doesn't matter which way you go, but if I move, let's say, the 3y to the left side, we're going to wind up with 5y equals 0. So the corresponding straight line solution there would just be y equals 0. And I'm going to highlight that just so we have it at the forefront if we need it later. And so the eigenvector that goes with that, we're going to choose a value. Y is always going to be 0, so choose a value for x. Obviously 1 is an easy choice. I'm going to highlight that as well. So that's going to be the eigenvector that corresponds with the lambda value of -3. All right, then let's take a look at 2 as the other lambda value. So when the second eigenvalue is 2, we're going to wind up with -3, let me write that matrix out again, -3, 0, 0, and 2, and then times xy is equal to, this time it's going to be 2 times xy, and then expand that, we're going to end up with -3x equals 2x. And then we also, if we use the other equation, it'd be 2y equals 2y. Again, that's the identity, so that doesn't really do much for us. But the first equation, we're going to wind up with, if we move that over, we're going to wind up with 0 equals 5x, for example, or just x equals 0. So the straight line solution that corresponds with that eigenvalue is going to just be x equals 0. And then let's go ahead and write out a vector that we can use to go with that. This time x is always going to be 0, so just let's choose 1 for the y value for that eigenvector. And let me highlight this just because we want to have it easy to see in just a moment. Now, remember how we write out our general solution. So we know that, well, let's do it this way. Let's write out the particular solutions first. So for the, let me come back up here, and you can write it wherever you like on your paper, but I'm going to put it up here just so these are together. The first particular solution then, remember that it's always e to the lambda t times the eigenvector. So if it was -3 for the lambda, it's going to be e to the -3 t times the eigenvector of 1, 0, whereas the other particular solution is going to be e to the 2t and then 0, 1. And so those are going to be my particular solutions. If we put that together using linearity, my general solution then, remember, is going to be y of t is equal to k1 times the first solution plus k2 times the second solution. And that would be my general solution right there. Now, the last part of this question, it said to sketch the phase portrait. Now, we can do this a little bit by hand, and then I'm going to have you look at what it would look like using technology, but let's just talk about which case it would be. So notice that the eigenvalues were opposite signs. That means we're looking at a saddle. So let's go ahead and make a quick little sketch of what this would look like. Don't forget that your straight line solutions, remember I highlighted those, the straight line solutions were y equals 0 and x equals 0. Let me not write that using a bracket. Let me just kind of write those separately. So y equals 0 went with the first lambda, and then x equals 0 went with the second lambda. It was 2, I think. Okay, so we know that because those are opposite signs, we know we're going to get a saddle, and let's take a look at what this graph is going to look like. What I would start off by doing is drawing those straight line solutions. I think that kind of helps you get everything situated. So y equals 0, of course, would be the x-axis. So that means that we know that we're going to have a solution. Let me use a different color here. We know we're going to have a solution along the x-axis. And what you want to think about is, because that lambda value is negative, that means that, remember, look back up here at your general solution or at the particular solution, either one, but you've got a negative lambda value. That means that as t gets larger, these values are going to get smaller and smaller. And so the values here are going to approach 0. And let me say that one more time. So remember, this went with the eigenvector of 1, 0. And so y is always 0. That's not a question. But what's happening with the x values as t gets large? Well, as t gets large, remember that these x values are going to get smaller and smaller. And so for the straight line solution, y equals 0, you're going to be approaching the origin. And that's going to be that part of the saddle that goes towards the origin. Now, what's happening with the other eigenvector? Well, that would be x equals 0. Of course, we know that that is the y-axis. Oh, that's not very straight. Let me try that again. We know that that's going to be on the y-axis. And let me adjust my screen just a little bit here. And we know the eigenvector that went along with that solution was 0, 1. We know that x's are always going to be 0, so that's not the question. But this time, what happens as t gets large to the y components? Pop back up here and look at your particular solution. As t gets large, these numbers are just going to get large because you have a positive eigenvalue. So those values are just going to get bigger and bigger. And so accordingly, so are your y values. So that means that the arrows are going to point away from the origin this time. And that's what creates that saddle. Remember, they're going in opposite directions. So to get the rest of what's going on, you just kind of want to draw some solution curves that follow what the arrows are doing. So let's start with quadrant 1. You can see that the x's are approaching 0, but the y's are getting larger. So that means your solution curves are going to kind of follow in this direction. Same thing in the second quadrant. Just sort of follow what those arrows are doing. And then in the third quadrant, your y's are going to go down to negative infinity while your x's approach 0. And in the fourth quadrant, same thing. All right, and that's your saddle. Now, real quick, let's just take a look at what this looks like using technology. I think I have it pulled up here. Let me go back to Google. Here it is. So this is the slope field, or the phase portrait plotter that includes the straight line solutions, which is kind of my preferred version of it. You can see along the x-axis, notice those arrows in red are going towards the origin, and along the y-axis, notice those arrows in red are going away from the origin. You can just kind of see what's happening in blue with the rest of the saddle if you follow along with those arrows. So that's basically it. We're going to do a little practice with this in class tomorrow, just looking at some of those other cases, what to do with those when those eigenvalues have values that are both positive or both negative, and get into drawing some of these tomorrow. So I'll see you then.